Yikes, and only 22 people are here. I'm gonna get an earful. Okay. Anyways, thus for all x, x is an S implies x is an S, so S is a subset of S. Okay, so we have proven these two statements. The empty set is a subset of any set, and the set itself is a subset of any set. Any questions here? We did get to use, these are nice applications of proof by like vacuous arguments and trivial arguments. Okay, great. That's another thing done. Yes, we should have a definition. A proper subset is a subset which is not equal. Right, so I just will say a subset is a proper subset if there's an element of B which is not contained in A. So A is a proper subset of B if A is a subset of B and there exists an X in B, X is not in A. What made you realize you did not have the class recording? I don't know, I just remembered that I never turned it on. Silly me. Okay, we're going to get into some interesting stuff in just a minute, but I want to quickly, is the empty set a proper set? The empty set is always a proper set unless it's the subset of the empty set, right? So the empty set is always is a proper subset of S if S is not the empty set. Of course, I also have the empty set as a subset of the empty set, but then it's not a proper subset because there are no elements in here that are not in here. So the empty set is almost always a proper subset. Does that make sense? Just follows from the definitions, right? Okay. Messed it up again. Okay. Size of a set or cardinality. Okay, so definition. If there are exactly n distinct elements in a set S, we say S has cardinality n, and we use these absolute value symbols to denote the size of a set. This is equal to n. If a set is not finite, oh, and such a set will be called finite if it has exactly n distinct elements. If a set is not finite, then it has infinite cardinality. We'll deal with a lot of these infinite sets later on in this chapter. We already know a bunch of these. the integers, the rationals, the reals, the complexes all have infinite cardinality. None of them are finite sets. Okay, now we get to what I was really excited about today with 20 minutes remaining. Perfect. Are we going to talk about the different sizes of infinity in this class? Yes, absolutely. It's a very exciting time. I predict we do that in a week and a half, or maybe a week, probably a week and a half. I agree. I wholeheartedly agree. Okay, so now we are going to talk about constructing new sets out of old sets. And there's one kind of truly blessed way of constructing a new set out of an old set. And that's called the power set. Okay, so definition. Given a set S, the power set of S denoted P of S is the set of all subsets of S. Okay, so here's an important point that I want to really distinguish, and we'll distinguish this more in the upcoming things. Being an element of a set is very different from being a subset of a set, because those are different sort of classes of objects, so to speak. So we'll do some examples in just a moment, but what I really want to kind of get at is that if I take a set S, there's one collection of ideas, which are what are the elements in this set. There's another collection of ideas, namely what are the subsets of this set. And what the power set of a set is it's the set whose elements are the possible subsets. We do not count, so to each element, there exists a subset which consists of that element, but that's a different thing from the element. So I'll do an example of that in just a moment. So for instance, let's let S be equal to the set with two elements, A and B. What are the subsets of S? Well, I always know there are two subsets, right? So there are actually more than what you've just written. There's the empty set. The empty set is always a subset, right? I also have the subset consisting of the element A. I also have the subset consisting of the element B, and I also have the subset consisting of the elements A and B. Okay, now for a quick test that goes to your question, Stefano. Which of the following statements is true and which of the following is false? If I write A is in the set A, B, is this true or false? This is true, good. If I write the subset or the set containing A is an element of A, B, is this true or false? Yes, this is false. And how about this one? A being a subset of A, B. This one is true. Okay, so hopefully this slowly starts to show you the difference between the notions of an element of a set and a subset of a set. And it's true that to every element of a set, you can associate a subset, right? Because to the element A, I can produce the subset, which is the set containing the element A. Right, so what this object is right here, this is a set containing a single object called A. but the elements of this set are just the elements A and B, and there is no element in here which is a set containing an element. So I'll do an example in just a moment that I think kind of clarifies things. So let me do one other kind of collection of things, which hopefully will confuse you a little bit, but after it confuses you, it starts clarifying notions. Okay, let's find the power set of the empty set. So what is the collection of all subsets of the empty set? Someone tell me a subset of the empty set. The empty set. And in fact, that's the only subset of the empty set. Okay? So the only possible subset of the empty set is this thing. This is a set which contains one element, and that element is the set which contains no elements. So here is my picture. No, it is not at all whack. It is beautiful. Okay, here is my picture. This is a folder. Usually I have like beautiful colored folders, but since I'm at home and budget cuts and everything, you only get this cheapo folder. So this is the empty set because it's a folder, and when I open it up, there's nothing inside. Here is a set with containing the element pen, because when I open it up, then, oh, look, there's a pen inside. So this isn't the empty set. But this right here, this folder, is the empty set because there's nothing inside. Okay? And then what this symbol means right here is the power set is a set which contains elements. And the elements that it contains are the subsets of the set that I started with. So what you should think of for this symbol right here, the set containing the empty set, is a nested folder. Now I have a folder, and when I open up this folder, there is indeed something in the folder. Ah, there's a set in the folder. And what's inside this set? Nothing. But these are not the same, right? A folder containing an empty folder is not the same thing as just an empty folder. This would work better if I had, you know, if y'all were in the classroom with me and I had 8 different colored folders. But is this okay so far? So in particular, okay. Any questions so far? See, it's not as whack as you thought at first. Right. Okay. Now let's go a step further. What is it in Inception? It's like, we're going to go a level deeper or something like that. What is the power set of the set containing the empty set? Well, what's always a subset of anything?
The empty set.
The empty set is always a subset. But this set isn't empty, right? Exactly. I also have to have itself. The set containing the empty set is also a subset of the set containing the empty set. So what this is it's something like this. I'm now going to have further folders. This set should be thought of as follows. It is a set such that when I think about, well, I need even more folders. The empty set is a subset of this set, and it also contains a set which contains the empty set. Is this okay? It's a set which contains both the empty set as an element and a set whose only element is the empty set or the empty folder. Yeah, exactly. So here is the picture. I need more folders. Okay. Okay, so this yellow manila folder is the outermost braces. Okay, so when I open up the outermost, so sets can be elements. It's just that you have to distinguish between the ideas of an element of a set and a subset of a set. But I can still make a new set whose elements are subsets. You just have to keep in mind at what level you're discussing. You have to, in any given situation, you have to ask, am I talking about a subset of the given set or an element of the given set? Okay, so this yellow folder is going to be the outermost folder. And when I open up this outermost folder, there are going to be two objects inside. So I open this up, and there are two objects inside. One of them is the empty set. You have to pretend that this is a folder with nothing in it. So this copy of the empty set is this thing right here. This copy of the empty set is inside this big folder. The other object inside this folder is a set such that when you open it up, the only thing inside is the empty set. And then this is the empty set. So this pair of nested folders, a set containing a set whose only object is nothing, is this guy. And both of these are objects inside the power set. But wouldn't that be kind of a contradiction, because the set inside would be something inside the empty set? I'm not exactly sure how to digest that. So where are you saying the contradiction is? Essentially, one way to think about it is in each case, you open up another layer of the folder. So when I open up this set, that's opening up the first folder, and I see two elements. One is the set which has nothing in it, so I write it as the empty set. And the other thing is a set which contains one element, and the element of that set is the set which contains no elements. So an element can be a set, but a set cannot be an element. No, a set can be an element. In this case, this set, I mean, that's the whole principle of what a power set is. A power set is the elements of the power set are the subsets of the set S. So this is the, in a certain sense, the best example that I can give here, right? Like, I mean, I can give you other examples of power sets, and we'll do that plenty. But let's for instance do one more. Okay, what is the power set of the set containing the empty set and the set containing the empty set? So let me do this example, and then I'll go back to Catherine and Rohan's questions. Okay, so let's list out the sets which are subsets of this set. Okay, so here's the set that I am interested in. Its elements are the empty set and the set containing the empty set. Okay, first thing that always goes in when you are taking the power set is what?
empty set.
The empty set always goes in. The empty set is a subset of this thing. But here's a very weird thing. The set containing the empty set is also a subset of this thing. Because the empty set is also an element here. So the next thing that goes in is the empty set. Or the set containing the empty set, sorry. There's another subset because there's another element. So the set containing the empty set is also a subset. Because these are two elements. You should think of this as being like the set containing A and B. It's just I replace A with the empty set and I replace B with the set containing the empty set. So I also put in this thing in here. The set containing the empty set. And then lastly, the entire set is a subset of any set. So the last thing that I put in here is the set containing the empty set and the whole, this thing. The set containing this. Is this okay? Maybe let me do another example of power sets where it's not this challenging stuff involving sets that look like the empty set. So here's a more basic example. I want to go back to these questions. Okay, so if I'm taking the power set of the set containing the elements 1, 2, and 3, right? Then I'm going to list all the subsets. Well, one subset is the empty set because the empty set is always a subset. I get another subset for each element in here. I get the subset 1, right? Because 1 is an element of the set 1, 2, 3, and the set containing 1 is a subset containing, or is a subset of 1, 2, 3. Do you see this relationship? If 1 is an element in here, then the set containing 1 is a subset. Since the set containing 1 is a subset, it is now an element of the power set. Right, right. Here's another thing that goes in here. So remember, if you're checking whether something is an element, you just say, is this symbol inside here? If you're checking with a subset, you open up the subset and you have to check, is every element of this set also an element of this set? So the subset containing the element 2 is also a subset here. So 2 goes in. Sorry, let me segment this off. Also 3. The set containing 3 is a subset of the set containing 1, 2, and 3. Okay, but there are more subsets. There's also the set containing 1 and 2. There's the set containing 1 and 3. There's the set containing 2 and 3. And lastly, there's the set containing 1, 2, and 3. All of these are subsets of this set. Is this okay? Would it be incorrect to also have to rewrite all of those with the set 0 also? I'm a little confused. What do you mean? You're asking me if the empty set belongs in all of these sets? So the answer is I don't need to rewrite, so like 1 comma set. I'm sorry, I still don't quite understand. Oh, it's 10:10, but I'm happy to continue answering y'all's questions. So, unfortunately, I still don't understand your question though, SJ. So the point is, I am listing here all of the subsets of this set. And so the empty set only appears once on this list. However, the empty set is also a subset of each of these individual sets. That's true. But you don't need to put it in this list because it doesn't appear, like we were only asking about the subsets of the set containing 1, 2, and 3. And the possible choices are, I pick no elements, I pick one element, I could either pick 1, 2, or 3, I pick 2 elements, here are all the ways to pick 2 elements, and here are all the ways to pick all 3 elements. An empty set is always a subset of any set, yes. That's right. The very first page? What do you mean the very first page? Of the lecture. Is that here? No, that's not here. That's here. So I agree that it's very confusing the first time that you see it. We will be working with that, definitely. So what we will do is we will do more examples and work more on this example of power sets of empty sets. Yep. Mm-hmm. Yep. Have a nice day, everyone.
Thank you too.
Thank you.
So long. Yep. See you all on Friday. We'll discuss more of this subsets of the empty set stuff on Friday, so don't worry. The office hour is Monday, Tuesday, or Thursday. So I'll have office hours tomorrow. Mm-hmm. All right, so long.